Let us discuss in this tutorial session the different types of ray diagrams for wavefronts. Basically, we can classify like this: wavefront, reflected wavefront, refracted wavefront. Reflected wavefront, in this case, plane mirror, and here spherical surfaces. Naturally, spherical mirror means concave mirror, convex mirror. Similarly, we can have the refraction through plane surface and through prisms. Now let us discuss the first one, how the wavefront is represented in a plane surface. Let us consider a plane surface like this. This is the refracting surface, and below which we have the non-refracting surface. Non-refracting surface. Let us consider X, Y as the reflecting plane. And these are the normals. Draw a vertical line, and that will be the normal. N, and this is perpendicular to the plane surface. Let us consider a ray SB. Yes. B, and another parallel ray, so that makes the beam of light. Let me call it, that is P. So the wavefront here is, this is the wavefront, which is perpendicular. Okay, so let me call AB is the incident wavefront, and now it is going to reflect like this. In the same way, this also get reflected. And let me draw normal N dash. Okay. Now this is the angle of incidence. Angle of incidence is the angle subtended by the incident ray to the normal. And here, this is the reflected ray. From the normal, reflected ray. So we know this is 90 degree being normal, okay, and here this is NBA and NA, let me say this is, now this is also I according to the diagram. And R is this much. Now we need to draw the wavefront, that is the reflected wavefront, which is perpendicular. Let me call it D, and this is C. So AB is the incident wavefront. DC is the reflected wavefront. DC is the reflected wavefront. XY we already know, that is the reflecting surface. Reflecting surface. NB and N dash C. NB and N dash C, they are the normal. Normal means the hypothetical 90 degree line. Normals. Normal to the reflecting surface. Reflecting surface XY. Okay, and I is the incident angle or angle of incidence or reflected angle. Now when this is R, this is also equal to R. You know, now we are able to identify the two triangles ABC and BDC. They lie on the same plane and the same base BC. So these two triangles are congruent. So triangle ABC is congruent to triangle, equivalent to triangle what? That is BDC. This is ABC and DBC. Otherwise, keeping the right angle, you can call it BAC. Triangle BAC is congruent to triangle BDC. So the corresponding angles should be equal, corresponding sides are also equal, right? So in this case, I is equal to R according to the law of reflection. Angle I is equal to angle R. And the plane XY, then the normals and the incident ray and incident wavefront and the reflected wavefront all lie in the same plane according to the first law of reflection. I hope now the diagram is very clear. Okay? Right. Now we can draw the same diagram applicable for the convex and concave mirrors also. Let us draw the concave mirror, that is reflected wavefront in when it strikes on a concave mirror. Let us draw a concave mirror, and before that always draw the principal axis, then draw the concave mirror. This is the non-reflecting surface and the left hand side is reflecting surface. Now the incident ray, they come like this. Now which is the incident wavefront? The perpendicular line. This is the incident wavefront. So let me call this as B, right? And you know this is the pole of the mirror. Now they get, when they come from the distant place, they are parallel and we are drawn the incident wavefront. So AB is the incident wavefront. AB is the incident wavefront. Now they get focused at F, that is the focal point, is it not? And principal focus, the light traveling through the principal axis is reflected in the same direction. Okay, so they meet. So it is a converging type because concave mirror. So they converge at F. And what about the reflected wavefront? The reflected wavefront can be represented like this. That should be parallel to the what? The concave surface. So you have to draw like this. Okay, and this is the reflected wavefront. Are you able to follow? So reflected wavefront, what is your observation here? Since it is a spherical surface, and this will also be it will be of spherical nature. So reflected wavefront is spherical. Is it clear? Right. Now, when a plane front strikes the convex mirror, let us see what does it happen. Here, convex mirror. Let us consider the principal axis. Always draw the principal axis first. Then the convex mirror. So the curved surface is non-reflecting on the other side. On the left hand side, it is reflecting types. So what happens here? The beam of light comes and strikes the convex surface like this. Let me call it, this is the incident wavefront. This is incident wavefront. Now since the surface is convex and this is a diverging mirror, so the focal point is on the other side, so it is going to refract like this. Okay, so you can show this as a dotted line also. This is the focus. From here it will go like this. Okay, now continue. Similarly it goes. So this is the that is refracted ray, and you have to draw the refracting surface. So the refracting surface will be, refracting wavefront will be like this. Okay, so this is parallel to this convex surface. So this is the reflected wavefront, and this is also spherical. Okay, and this is the P, that is the pole of the convex mirror. Is it clear? Right. Now let us see the refracted wavefront when a plane front goes from rarer to denser medium. So now we are going to discuss the refraction. Refraction from where? From rarer to denser medium. Let us draw the refracting surface. So this refracting surface xy is the refracting surface. xy is the refracting surface. Now let us draw a normal. n dash, that is perpendicular to the refracting surface. So n dash is the refracting, normal to the refracting surface. Normal is nothing but the perpendicular line, which is hypothetical. Right? Now the incident ray, and this is a rarer medium. Okay, so its velocity, the light traveling in rarer medium is v1, then denser medium, it is v2. So you can represent the rarer medium as 1 and rarer medium as denser medium as 2. So refractive index of rarer medium is mu1, refractive index of denser medium is mu2. Now the light is incident obliquely on the refracting surface at an angle I, that is the incident angle. So SA is the incident ray. Right, and a parallel beam of light that also strikes the incident surface. So this is also, you can call it Q or R you can put. Okay, so it strikes the surface at C. So RC is also incident ray and they are parallel. Now this is the incident wavefront which is perpendicular to the direction of propagation of light. So perpendicular, and therefore AB is the what? The incident wavefront. AB is incident wavefront. Incident wavefront AB. And what about the distance BC? That is the, we know S is equal to VT. The displacement, S is equal to VT means displacement is equal to velocity into time. So in this case, what is the velocity of light here? V1. And what is the displacement? We are talking about this BC displacement. So BC is equal to velocity V1, and you can put T here. Okay, so V1T. So BC is equal to V1T, or it can be replaced by tau also. Now let us talk about the refracted beam. The refracted beam, since the light travels from rarer to denser medium, it gets deviated towards the normal. So that is R. Okay. Now the first light, the first wavelet, the primary wavelength. From the primary point, you are able to get the secondary wavelet. So that can be an arc like this. And where from, let me say this is D, this point is D. So here, by the time B comes to C, the ray A has reached D. Okay. So you can draw a tangent like this. And this is the refracted wavefront. Okay. So DC is the refracted wavefront. Refracted wavefront. So AB is the incident wavefront, and DC, let me highlight like this, DC is the what? The refracted wavefront. Now if it is R, this is also R. Okay, and this is I, this is R, and this is also I. Okay, because this A, D, C, and what about this? This is A, B, C. We have the two triangles here. And we know already this is a rarer medium, this is denser medium. AB is the incident wavefront, DC is the refracted wavefront. Are you able to follow? Now what is the distance travelled by A to D? A to D is AD is equal to V2 into T at the same time. Is it not? Because the velocity of light in denser medium is V2. So we have put V2 into T. Okay, so AD is equal to V2 into T. What about this one? BC is equal to V1 into T. So this point is very clear. Okay, so based on this we derive the equation. We find out a sin I by sin R, that is mu. What is sin I here? This is I, and this is AC is the hypotenuse. You can mention that one also. AC can be taken as the hypotenuse. Okay, so in that case, now, and this is 90 degree, you know very well. Okay, this is 90 degree and this is also 90 degree. Okay, because it is a tangent to the curve, 90 degree. Okay, now sine I means what? That is opposite by, which is opposite? Opposite is BC divided by AC, is it not? Therefore, sine BC, sine I is equal to BC divided by AC. And what about sine R? Sine R is AD by AC. Sine R is equal to AD by AC. We already know BC is equal to V1T and AD is equal to V2T. We can substitute in terms of V1T and V2T for BC and AD respectively. Therefore, mu is equal to sine I by sine R. That is equal to AC can be cancelled. Now we have BC by AD and BC is nothing but V1T. So V1T divided by V2T. So T can be cancelled. Therefore, it is the ratio of light traveling in rarer medium and V2 ratio of, velocity of light traveling in denser medium. Okay. Now, let us try to draw the refracted wave front when a plane front goes from denser to rarer. So that should be considered here. So refracted wave front, refracted wave front from when the light travels from denser to rarer. Rarer medium. Okay. Right. Now let us consider the refracting surface xy, and here this is denser and this is rarer. So this is 2, this is 1. So V2, V1. Okay. You know very well that is the velocity of light in denser medium is greater than rarer medium. That you should note down. Now, here, that is V1 is greater than V2. Okay. So, in this case, the light travels, and before that you had to draw the normal. Draw the normal. So this is the normal, and let me draw an incident light obliquely, and parallel to this another ray is striking on the refracting surface. Now this is the incident wavefront which is perpendicular. Okay, so let us call it AB. So AB is the incident wavefront, and we know very well it travels away from the normal, since it is traveling from denser to rarer. So away from the normal. So actually it should have gone like this. Now it has deviated in this way. And similarly, now let us draw the diagram here. This is the refracted, and assume that from this we have got the secondary wavelet like here. This is the arc, the wavelet. So tangent to this is this one, which is perpendicular also. Now this is the refracted wavefront. Okay, so let me call this as C, so this as E. So EC is what? The refracted wavefront, right? And what about AB? AB is the incident wavefront. AB is the incident wavefront. Okay, right. And let us try to label I. This is the incident angle. What about this? This one is the refracted angle, angle of refraction. Now similarly, the distance traveled here is BC, okay, which is nothing but V2t here, and here V1t once again. By convention, we always take one as rarer medium, two as denser medium. Okay, right. And what about AE? That is also distance traveled by that particular first wavefront, or the primary, the secondary wavelet here, because we already know the secondary wavelet, the overlapping of secondary wavelet, okay, is the wavefront. Is it clear? So probably from here it forms a first wave. Let me indicate this by a small arc, and another refracted ray, it forms a small arc. Another refracted ray, it forms a small arc. Another refracted ray, it forms a small arc. Another is a small arc. I hope now you should be able to understand this. So the overlap or the complete envelope of the secondary wavelets, that is the wavefront. So here it is the refracted wavefront. Is it clear now? Right. Then let us draw when a plane wavefront is refracted by a prism. Okay. Plane wavefront. Refracted by a prism. Let us consider this as a prism. So we have A, B, C. BC is the base of the prism. AB is the first refracting surface. AC is the second refracting surface, or the emergent surface. Okay, emergent surface. Here, the wavefront let me consider the wavefront here. The light travels like this. Now this is the wavefront, incident wavefront. Let me call A, B, C, D, E. So DE is the incident wavefront. Actually we should draw obliquely, but for your better understanding I have drawn like this. Now they get refracted, okay, and this is the refracted waves or rays, and this line is the refracted wavefront. Let me call it D dash E dash. Are you able to follow? So D dash E dash is the refracted wavefront. Okay. Now let us try the plane wavefront, how it is refracted by a convex mirror. So plane wavefront refracted by a convex lens. So this is the, always draw the principal axis first and convex lens. Now draw a parallel beam of light like this. Okay, so this is the incident wavefront. Which is incident wavefront? AC. So AC is the incident wavefront which is perpendicular to the direction of propagation of light, and through the principal axis it goes, and this is the pole of the lens, that is the center point of the lens, and being converging lens it gets converged at the focal point like this. Okay, now this is the focal point. And what about the refracted wavefront? It will be a curved surface like this. Are you able to follow? So we can call it A dash C also for your better understanding. So A dash C dash curve is the incident, refracted wavefront. Is it clear? So what are the types of mirrors and lenses or the surfaces we have discussed so far? Let us have a fast summary. The wavefront that can be passed, incident on the reflected surface and the refracted surface, reflecting surface and the refracting surface. When we say reflecting surface, we can talk about plane mirror and spherical mirrors, concave and convex. Similarly, in the case of refraction, we have plane surface and a prism. Okay, and we have got the spherical surfaces also. Spherical surfaces, which is nothing but lens. So convex and concave. Okay.